Okay, welcome to your Chapter 12 introductory video. This is Thermodynamics, why chemical reactions happen. And that last statement is why this chapter is so incredibly important. You'll be able to predict why chemical reactions happen. So some of the learning goals in this chapter, make sure you can accomplish these by the end of the chapter. We'll be introducing the concept of entropy. You'll need to understand it conceptually and also be able to make calculations. The other major concept is free energy, and this is hugely important, one of the single most important concepts in all of general chemistry. We'll be doing calculations with it. You'll also need to understand it conceptually. So let me ask you a question here. What do these have in common? And of course, you might guess by looking at these and by the title of the slide that kind of all of these happen without any sort of external force keeping them going. Of course, things have to be initiated, but other than that, they're spontaneous, we say. They continue to happen once they start without any real external force. And that's one of the keys. So they're all spontaneous. That's the key, that word, that spontaneity means. What do you mean? What do we mean when we say that? It proceeds without outside intervention, if you will. Now, one thing to keep in mind, it does not mean they happen fast. So rate is not being considered here. That has nothing to do with spontaneity. That is the next chapter. We'll talk about the rates of reactions. You can have a spontaneous reaction that is incredibly slow. It's also important to realize, and these are terms that were introduced in the previous General Chemistry 1, and that is spontaneous reactions can be endothermic or exothermic. A lot of people tend to think that spontaneous reactions must be exothermic, energy's being given off. That's not always the case. That's important to realize. So most people know from a very early point in their life, probably middle school, if not certainly high school, the first law of thermodynamics. First law of thermodynamics says that energy is neither created nor destroyed. Everyone knows that, remembers that, but not a lot of people recall or ever learned what the second or third law is. So let's talk about that. The second law of thermodynamics states that entropy of an isolated system always increases for a spontaneous process. So think about the previous slide and what we talked about, air rushing out of a punctured tire. Well, before we say that entropy increases, let's make sure we understand what entropy is, and it's down here. Entropy is a measure of order or randomness, okay? We say a system has high entropy means it's much disordered, okay? So, entropy of an isolated system always increases. Increase in disorder, disarray. Okay? The convention we're going to use for that is an increase is going to be positive, greater than 0. Increase in randomness. So when we think about entropy, we have to think about a high entropy system is much disorder. Increasing in entropy means increasing in randomness. Okay, so now let's go back to this. Isolated system always increases. Entropy of an isolated system always increases for a spontaneous process. Think about this. Ice cube melting. Ice cube's very structured and ordered, and it's becoming a liquid puddle. So you would think that solids are the least entropy, gases having the most entropy, right? And air rushing out of a punctured tire. Air's confined to this one space. As soon as the air rushes out into the atmosphere, it's free to move about much more randomly and freely. You can see how those are very much increases in entropy. Now, we also learn about the entropy of the universe and say that entropy is always increasing. So realize that entropy for an isolated system can decrease, not for a spontaneous process, but can decrease for a non-spontaneous process. But that would have to only occur in a situation where the entropy of the surroundings, the rest of the universe from your isolated system, would have to be increasing. Okay, so a lot of people forget to make that connection. So you can have an isolated system that decreases in entropy, becomes more ordered, but the surroundings then would have to become more disordered. And ultimately, you can calculate entropy down here by simply, same way we did with delta H in Gen Chem 1. Final enthalpy minus the initial enthalpy is your delta H. Now, entropy is a kind of an abstract concept, so let's spend a minute or so talking about this. And one thing we can use as an analogy is these two gases separated by a chamber. This is very similar to what I did with osmosis. And osmosis happens because of an entropic effect. So imagine two gases separated, say whatever, hydrogen and oxygen gas, or they both look like monoatomic gases, say helium and argon. And as soon as we open that port then here, these gases will diffuse back and forth, and ultimately you'll have something that looks like this. And I said to you in osmosis, just think about just statistical probability and randomness, and ultimately it's going to wind up being, completely random. Well, entropy can really be explained by energy, because you might ask the question, well, why though? Why does the universe care that those gases are kind of randomly dispersed? It's because of energy. Now, what you have to realize here is, so this is at a particular temperature, that these molecules have different energy. Because we learned in chapter 10, when we talked about gases, ideal gases, that at a given temperature, the lighter molecules will be moving faster and therefore have a higher energy. Remember, kinetic energy is 1/2 mv squared. So the mass of the gas molecule is very important, and they'll have a higher velocity and they basically have a higher energy. So that's what is really driving this, getting to a thermal equilibrium. Energy is equilibrated. No different than why you can say, hey, I put a shopping cart at the top of a hill, and why does it randomly just fall to the bottom of that hill? Well, it's reaching a lower state of energy. I tell my Gen Chem 1 students, everything in nature and science can be explained and happen, reactions and all these things, because things move towards a lower state of energy. Why does a building crumble? Because it needs to increase in entropy, because it takes energy to hold that building together. That energy wants to dissipate. So that's the easier way of thinking about it, rather than saying, well, why do we have this random distribution of molecules? It's really the random distribution of energy. The third law of thermodynamics is the entropy of a perfect crystal is zero, absolute zero. And this is one of these ones where we're basically simply trying to define a system and give us a way providing a reference point. I use this analogy of the periodic table. We decided that on a unit of AMUs, atomic mass units, and we decided carbon would be exactly 12, because carbon 12, I should say, because it has 6 protons and 6 neutrons, and their masses are very close together. Now, they don't, obviously, there is no unit. We created AMU. They don't weigh 1 gram. We decided, okay, they have comparable masses, whatever it is, 10 to the minus 28 kilograms or whatever. We decided it was 1, so we made carbon exactly 12, so we can make a reference point to compare everything to. That's all we're doing here. We picked the most ordered thing we can come up with, a perfect crystal. Okay? That means there's no mistakes in that crystal. It's perfectly ordered, has a value of 0. That's our baseline. And we're going to tabulate things. And we'll look at this in class. We're not going to do it here on the video, but basically you'll see the table of entropies, and it'll be for 1 bar of pressure and 25 degrees C. Now, let's look at a couple qualitative guidelines for entropy. We're going to start by doing this qualitatively, then we'll move into quantitatively, and we'll handle that mainly in class. But one thing that might jump out at you right away, and I mentioned this already, is the entropy of a gas is going to be much greater than the entropy of a liquid, and certainly greater than the entropy of a solid. And you can see that here when you compare bromine gas to bromine liquid or iodine gas to iodine solid. This is your units for entropy. So that shouldn't be that surprising. And why do we see that? Well, think about it. Gases have fewer restrictions on motion. Gases can do this all over the place, right? That's my gas molecule. When you think about a crystal, a solid, it's confined within a particular array. And then a liquid is somewhat in between. So this shouldn't be that surprising to you. Another thing to think about is very simple to really think about, and that's why I chose this for the video also. A solid or liquid dissolving, we would ultimately see that as an increase in entropy. So when you think about a solid or liquid, now they can disperse much easier within that liquid, and that is what gives us that greater entropy. There's really nothing to say more than that. Just looking at the figure here, here's your pure, let's take ammonium sulfate as a solid. That's its entropy. Once it's dissolved in water, those ions are free to move about. You see an increase in entropy. Now, you can actually mathematically predict changes in entropy. This particular, I'm sorry, not mathematically, it's just still somewhat qualitative. So we look at this particular reaction here, and you see it has a large entropy increase. So that should say to you now that, okay, we're increasing in randomness. So how we see, by looking at that reaction, you might predict that, not the actual value, but you would predict, hey, it's going to be positive. Well, how do I know it's going to be positive? Well, look, I'm going from a solid on the reactant side. And what's on my product side? A gas. There's also a solid there, but that solid is smaller now. Okay. And we're also going from one molecule to two molecules. I'll use the word molecules, which is not entirely correct, but because this is a salt crystal, and so is this. But you get the idea, is that that's going to be more random. So the more atoms you have dispersed and unconfined and restricted. So if you have one crystal and that breaks down into even two solids, you would expect that to be more random. So it's not surprising you see a positive value there. Now you can actually calculate entropy changes. And this is done very similar to the way enthalpy changes were done. Remember, we did delta H the same way. Products, summate all your products and subtract the summation of all your reactants. So we'll do this in class. I'm not going to do a calculation here, but I just want to introduce you. This is an equation that I won't give you on your equation sheets because it's the same equation over and over. You're going to see it again in this chapter, only with delta G. And all you have to remember is sum up your products and sum up your reactants and subtract the reactants from the products. Just remember that you have to use your stoichiometric coefficients from your reactions. So you would be taking these ones here, there's no twos here, and using those in the calculation. The last major concept in the chapter is free energy, and it's a major concept, and it constitutes a good part of the chapter. So, this is an important statement, neither entropy nor enthalpy alone can predict whether a reaction is product favored. Spontaneous product favored reactions can be exothermic or endothermic, so delta H is not going to help us predict that. They may increase or decrease in entropy. So delta S is not going to help us predict that. So what we're going to introduce is something called the Gibbs free energy. This combines H and S. So I will tell you that delta G does predict spontaneity. So here's the equation. It's an incredibly important equation, one of the most important equations you'll ever get in Gen Chem. Delta G equals delta H minus T delta S. A decrease in delta G or delta G less than 0, a reaction is product favored. So remember, delta H less than 0 is exothermic. And now delta G less than 0 is product favored. And you would think that exothermic would generally be product favored because you're decreasing in entropy, decreasing in energy. Remember that entropy delta S greater than 0, that's increase in randomness. That's an increase in randomness. Okay, so, and of course, if delta G increases positive, it's going to be reactant favored. And this is at a constant temperature and pressure. Now, you can calculate delta G the same way. Once again, this equation, I'm going to give you the exact same equation again, only with delta G. And what I've done, introduced now, this is actually standard states, tabulated values, because delta G changes constantly over the course of a reaction. This is tabulated values that we're going to be able to look up. And this is a really complicated concept that we're going to have to talk about and spend some time in class. Ultimately, this is a table that one of the most important tables you'll ever see in Gen Chem. I used to have this posted in my office next to my filing cabinet right next to my desk because I constantly refer to this. And we're going to spend an awful lot of time on this in class, but let me just point out to you here. You've got 4 conditions here. Always spontaneous, never spontaneous, spontaneous at low temperature, spontaneous at high temperature. And just to introduce you to this concept now in the video, it will always be spontaneous if you're giving off energy and you're increasing randomness, because those are the two things that favor. The universe wants to increase randomness, right? Disorder, and you want to reach a lower state of energy. So it doesn't matter what temperature it is. If delta H is negative, delta S is positive, it's always spontaneous. The other extreme is if it's endothermic, increasing in energy, and it's becoming more ordered. That's never spontaneous, which means you have to drive that reaction always with an input of energy. So the meaning of free energy, if you will, not all energy is used to do work. Free energy is a measure of the max amount of work that can be done. The energy changes that accompany the making and breaking of bonds can be divided into the delta G part and the T delta S part. And the important thing is to realize this is the total energy from the breaking of a chemical reaction, from the breaking and forming of bonds. So if you bring this over here, you can realize that plus that is the total energy. But delta G is the usable energy. So we take the total energy minus what this is considered is the unusable portion that is lost due to just randomness occurring. That's critically important to realize. And we'll talk more about that. But this is the unusable part of energy that is lost. So with that, that ends the video. See you in class, and make sure that you read this chapter and start looking at the material.